Welcome to the tutorial over Lesson 8.4, Graphing Rational Functions. Your new vocabulary is going to be rational functions, vertical asymptote, horizontal asymptote, oblique asymptote, and point discontinuity. Alright, so we have a few things to talk about. We have a vertical asymptote, meaning whenever your your x value can't equal a number. F of x has at most one horizontal asymptote, and we're going to talk about how you can actually tell what your horizontal asymptote is. You're going to be comparing the degrees of your numerator and denominator. Okay, so if your numerator is bigger than your denominator, that means you're going to have no horizontal asymptote. So for instance, we have x cubed plus whatever divided by x squared plus whatever. Okay, what you want to do is you want to look at the degree that's the biggest on the numerator and denominator. Okay, so the biggest we have on top is a 3, the smallest we have on bottom is a 2. 3 is bigger than 2, so that means there's no horizontal asymptote. Alright, so that's case 1. And again, that's horizontal asymptotes. Okay. Case 2, we look at the degrees and we have the numerator is smaller and the denominator is bigger. Okay, so you look at the degree of the leading coefficient, not coefficient, the variable. So say you have an x with a degree of 1 plus blah 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 divided by x squared plus blah blah blah. The leading coefficient on top is 1. Sorry, not coefficient. The leading degree is 1 and the biggest degree on bottom is 2. 1 is smaller than 2, so that means your horizontal asymptote is going to be 0. Okay, horizontal asymptote is 0. So that's case 1 and that's case 2. Then we have case number 3. Okay, what if the degrees are equal to each other? So we have the numerator and denominator degrees are equal. That would be like we have x squared on top plus blah 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 divided by x squared on bottom plus blah blah blah. Okay, and say they have like an 8x squared on top and then a 2x squared on bottom. If you take the degrees and they end up being the same, that means you're going to revert to the leading coefficients on those two x values. You would take 8 divided by 2, which is 4. So that means your horizontal asymptote would be at y equals 4. Okay? So there's 3 cases. One where the numerator's top is bigger, one where the denominator is bigger, and one when they have the degrees are the same. If you take a look at these pictures, here we only have one vertical asymptote, here we have 2 vertical asymptotes, and here we just have 1. So these are all different rational functions that you're going to learn how to graph in this video. Alright, so example 1, we're going to graph f of x is equal to x cubed divided by x plus 1. So you can always check in your calculator, but sometimes it's easier to see what your horizontal and vertical asymptotes are without actually graphing it in your calculator. Okay? So you actually end up getting this really weird looking graph. A couple things I want you to look at is how you find your vertical asymptotes. And that means that our denominator cannot equal 0, so we have x plus 1 equals 0. That means x cannot equal negative 1. So at negative 1, you would draw your vertical asymptote. Okay, like so. The next thing you want to check is what are your horizontal asymptotes? So this is where the cases come in. We have x cubed over x plus 1. On top, we have the biggest degree is a 3. And on the bottom, we have the biggest degree as a 1. 3 is bigger than 1, so that means we have no horizontal asymptote. So that would actually be like case number 1 for the horizontal asymptote. Now, you can always find different points to plug in, or you can go look at your table, and it will give you different points, so that way you can actually graph your function, which looks like this with your vertical asymptote. Alright, example number 2, average speed. A boat traveled upstream at R1 miles per hour. During the return trip to its original starting point, the boat traveled at R2 miles per hour. The average speed for the entire trip, big R, is given by the formula big R is equal to 2 times R1 times R2 divided by R1 plus R2. We're going to draw the graph if R2 is equal to 15 miles per hour. So the first thing we want to do is we actually want to replace R2 with 15 in our function. So I'm going to rewrite this as R is equal to 2 R1 times 15 divided by R1 plus 15. And the numerator becomes 30 R1 divided by R1 plus 15. So now that we actually have our function, let's talk about vertical and horizontal asymptotes. Okay, so our vertical asymptote would be where the denominator equals 0. So if we have R1 plus 15 equals 0, we subtract 15 from both sides. That means R1 cannot equal negative 15. Okay, so that's our first vertical asymptote. The next thing we want to do is we want to look for our horizontal asymptote. So I see I have 30 R1, which this has a degree of 1. And then I also have R1, which is a degree of 1 as well. This actually becomes like case number 3 we were talking about, where we have our leading degrees are the same. So when your leading degrees are the exact same, you have to look to your leading coefficients, which this would be 30 over 1. So we have a horizontal asymptote at, let's see, big R equals 30. Now that we know our horizontal asymptotes, we can actually graph our function. And you can actually get this from your graph. Just make sure that you zoom out enough, since we have our window that goes from negative 60 to 80 and from negative 20 to 80. If you don't zoom out, you'll end up not seeing the graph at all. Alright, it says, what is the R-intercept of the graph? So remember in the previous question, big R was represented our y, and little r1 represented our x. So when we're asking for big R-intercept, that means what is the y-intercept? Where does it cross the y-axis? So if we look at the y-axis, we see that our graph crosses at R equals 0. And our last question in the set, it says, what is the domain and range values and what's meaningful in the context of the problem? Okay, so values of R1 greater than or equal to 0 and R values between 0 and 30 are meaningful because we're talking about distance being traveled and a train's rate. So first of all, distance is going to be positive, okay? And then also our rate is going to be from 0 to 30, okay? We don't need any of this piece back here because this is talking about negative distance. So we would say the values of R1 greater than or equal to 0 and the values of R between 0 and 30 are meaningful. Alright, the next concept we're going to talk about are oblique asymptote. Another word for them are called slant asymptotes. which means we no longer just have vertical asymptotes and horizontal asymptotes. We also have ones that are lines as well. And we're going to show you how to find them. So, determining an oblique asymptote. If you have a case where your numerator is bigger than your denominator, meaning the leading degree, so we have a leading degree of 2 and 1, okay, so that means the numerator is bigger, you're not going to have a horizontal asymptote, so no horizontal asymptote, but that means you're going to have an oblique asymptote. So what that means, to find that oblique asymptote, you're going to have to take the numerator and divide it by the denominator. Now, this goes back to, I forgot what section it was, but we've done this before. Okay, so make sure we have x squared plus 0x plus 0. So that way you can make sure that you have this in line. Alright, so now you need to think to yourself, what times x will give us x squared? Well, we know that x times x will give us x squared. So we're going to subtract, and we have x times positive 1, which is a positive x. And we're going to put this in parentheses and subtract. X squared minus x squared is 0. We have 0x minus x, so that's going to give me a negative x here. Okay? So, one more time, we need to see what goes into x to make a negative x. And that's going to be a negative 1. So, we have negative 1 times x, which is going to be a negative x. Negative 1 times positive 1 gives us negative 1. We need to put this in parentheses and then subtract. Negative x minus negative x. These will actually end up canceling out because that turns into a positive. And we have a negative times a negative, which is a positive. So we have a positive 1 as a remainder. Okay, so our function is still x squared over x plus 1, but this actually gives me the equation of the oblique asymptote. So up here, if you set y equals to x minus 1, that's your oblique asymptote. So oblique asymptote is y equals x minus 1. Okay? And yeah, you kind of just forget about this remainder. All you want is what this equation is. Now you can actually graph this in your calculator, but I'm going to show you how to draw this with just asymptotes for now. Okay, so make sure you have this written down. I'm about to erase it. So we know our oblique asymptote is y equals x minus 1, and then we also need to find our vertical asymptotes by setting the denominator equal to 0. So we have x plus 1 equals 0. So x cannot equal negative 1. So if we have our graph, we know that x cannot equal negative 1, so draw your asymptote here. So let's say that's negative 1. And we have a slant asymptote at x minus 1. Okay, so we have x minus 1, and so we have our slant asymptote, like so. And since we're totally awesome drawers, it's going to look like this. It's going to follow your asymptotes, and that would be your graph. Okay, so the actual graph that you get from your calculator will look like this. The last kind of key concept we're going to talk about is a point discontinuity, meaning it makes your graph not continuous. You essentially have a hole in your graph. And what happens is when you take these factors and you cancel them out, you still can't have your x equaling negative 1 here, because it would make your denominator 0. But we end up getting this graph of just x plus 2 when we reduce, because we factored out and we canceled out x plus 1. Still can't equal x equals negative 1. So to represent that, this is going to be a line with a hole at x equals negative 1. Okay, so let's actually work some problems like this. So here we have a graph of f of x is equal to x squared minus 4 divided by x minus 2. Now, point discontinuities are really hard to show on a graphing calculator, so these you do actually have to do by hand. And you can get a general idea of the picture of what it should look like. Alright, so the first step is that we actually need to factor the numerator. Okay, so this is actually a difference of squares, so it's actually pretty easy to factor. When you're factoring a difference of squares, you take the square root of x squared, which is x. Square root of 4 is 2. And then you have opposite signs, plus and minus. Alright, and you're dividing by x minus 2. Now here, if we set the denominator equal to 0, we have x minus 2 equals 0. So we know that x cannot equal 2. Okay? However, we are going to cancel out this factor, and we're left with f of x is equal to x plus 2, where x cannot equal 2. So this turns into a line with a hole at x equals 2. So we have our y-intercept, and we draw our line. So this is x plus 2. And then wherever x is 2, if we plug this in, f of 2 is equal to 2 plus 2, which is 4. That means we're actually going to have a hole here about 4. So this is at 4, and we have our hole, and that would be our point, our removable discontinuity, or point discontinuity. Okay. And the actual nice graph that you might or might not get on your calculator looks like this. And that's it for our video. Thanks for watching.